Hi, my name is still Steven, and this is still the SIPGRAPI 2021 course on the plane-based geometric algebra. We're now at episode 3, titled Revenge of Infinity. Let's start with a small recap of what we've been doing up to now. So we've been looking at the Euclidean group, all of the distance-preserving transformations as the set of all k-reflections. We've seen that orthogonal k-reflections, also known as k-blades, are the invariants of those transformations and are ideal to represent our points, lines, planes, the elements of Euclidean geometry. We've also seen that we can compose these elements to get transformations between them. The product of 2 points gave a translation, a product of 2 planes gives a rotation or a translation, and so on. And we've seen that we can exponentiate these elements, take them to arbitrary powers. If you repeat a 2-degree rotation twice, you get a 4-degree one, and so on, to get transformations around those elements. We may have given you the impression that the Euclidean group holds all of the elements in PGA, but that's not entirely true. So we might have left out some line and a couple of points, and that's what we'll look at in this particular episode. So we'll be talking about infinity, how it leads to duality, how duality leads to orientation, and how all of it leads to forks. Let's get started. Like Leo taught you in the previous episode, to model the 2D Euclidean geometry, we will actually use a 3-dimensional vector space. So that's what we're rendering here. This is the origin of our 3-dimensional vector space, and this is the projective plane in which we will be doing Euclidean geometry. We want to represent our reflections and our point reflections as lines and points in this plane, and we will do so by representing lines as a plane through the origin in 3 dimensions. So you can imagine that if you take any line in the plane here, that you can always construct this plane through the origin. And in fact, when you do, and you take the entire set of those planes, you would have almost all of the planes through the origin, but not all of them, because there is of course one plane that doesn't cut the projective plane. So it cannot be associated with a Euclidean line, with a line in this Euclidean plane. What we'll do instead is we will associate it with an infinite line. Similarly, when we are representing points as bireflections, orthogonal bireflections, you can see this as every point in the plane being represented by a line in 3 dimensions through the origin. And as before, we could take all of the points in the plane, construct all of these lines, and we would get a set of lines through the origin that is almost complete. But it isn't complete. To make it complete, we also have to include all of these lines that do not cut the projective plane. And all of these lines will actually be associated with infinite points in 2 dimensions. So why would you want to do this? Well, it makes it so that when you do an intersection query that you always get an answer. So if we are intersecting this blue line and this red line, we intersect the planes instead. Since these 2 planes go through the origin, they will always intersect, and they intersect in this orange line. And this orange line is now the representation of the intersection point of the red and the blue one. So if the orange line cuts the projective plane, it does so exactly where the red and the blue one cut, and if it doesn't cut the projective plane, it's that exact point at infinity where the red and the blue line still intersect. So parallel lines intersect at infinite points, and you always get an answer. So that's one nice feature that you get when you add these elements at infinity. But it is not the only one. These infinite elements also enable duality. So remember that we just counted all of the planes through the origin, and we associated each plane through the origin either with a Euclidean line, if it intersected, or with the infinite line, the one plane that didn't intersect. So we can actually say that if we take the number of Euclidean lines and we add 1, then we get the exact number of planes through the origin. And similarly, with the lines through the origin, we did the same thing. We associated every single line through the origin, either with a Euclidean point if it intersected the projective plane, or with an infinite point if it didn't intersect the projective plane. Now, of course, for there are just as many planes through the origin as there are lines through the origin. You can easily see this because every plane has a normal vector, and you can associate that normal vector with a line. And so you have this unique map between planes and lines. But by adding the infinite elements, we actually make these counts the same too. So there are just as much Euclidean plus infinite lines as there are Euclidean plus infinite points. And because we have the same amount, we can now make a map. We can make a map that associates a Euclidean or infinite line with a Euclidean or infinite point. And this map is actually called the duality map. It works both ways. And so how does it work? Let me show you. We can take this green point. We can construct the line through the origin. We can construct a plane orthogonal to it and see where that plane cuts the projective plane. And so what we now get is this green line. And these elements are in a duality relation. So the green line is the dual of the green point, and the green point is the dual of the green line. Now let's do that for a second point. So we take this purple point, construct a line, construct the orthogonal plane, and see where it cuts the projective plane. So we now have these two lines, these two dual lines, the purple line dual to the purple point, the green line dual to the green point. Now what we want to do is we want to look at this intersection point of these two lines and do the same construction. So we want to construct the dual of this intersection point and see what happens. So when we do this, we will see that the dual of the intersection point is actually the line that connects the two original points. And this is really great because it means if you have a piece of code that can calculate this intersection point, then you can use this duality map and use the same piece of code to calculate a connecting line. So this really says, okay, if I want to find this line, then what I can do is I can dualize these both points. I can then take the intersection, and when I do, I will find the dual of the connecting line. And you can actually do this with any code you write in PGA. If you describe your code and it says something like, oh, this is the join between 2 points, then you could swap join and meet, and you can swap point and line, and you will get a new interpretation for the exact same piece of code. Again, keep in mind that this duality relation only exists because we add these elements at infinity. Right? If we don't add these elements at infinity, then there's not as many lines as there are points, and you can't make this one-to-one mapping. There is one last thing that these infinite elements do, and that is they unify rotation and translation. We've learned before that a translation is a reflection in two parallel mirrors, but you can actually also see it as a rotation around a point at infinity. And so, because we have these infinite elements, we can actually see rotations and translations as the same thing. These are the three superpowers of our infinite elements. So they enable exception-free intersections. They enable duality, which then unifies this meet and join. And they unify the rotations and the translations. But duality is something that actually we'll spend some more time on, because it also plays an important role when we are talking about dimension independence, as we did before in part 1. So what I have here is a two-dimensional drawing. Well, I actually have two. I have a robot arm on the left, and I have a floor plan on the right. And both of these drawings consist out of points and lines. Here are points on the corners and the lines connecting them. And so if you have a piece of code that makes these drawings, you would really have no reason to have two different functions to create points, or two different functions to create lines. But when you start thinking about dimension independence, the picture sort of changes. Because if we want to make a 3D version of this robot arm or of this floor plan, then we actually want completely different behavior. When we move the robot arm to 3D, we want points to stay points and lines to stay lines. But when we move the floor plan to 3 dimensions, that's not what we want. We want these lines to become our walls, so they need to become planes, and we want these points to become lines. And so here, we want the types of the elements to stay the same, and here, we want the types of the elements to switch. And we can actually quite easily do it, right? We could here define our points as d vectors and our lines as the joins of 2 points. And here we can define our lines as 1 vectors and our points as the meet of two of these lines. So here you get join lines, here you get direct lines, here you get direct points, and here you get meet points. And of course, these situations commonly occur both at the same time. So when we implement this, we can implement it in 2D, and if we pick our types correctly, we'll actually be able to move it to 3 dimensions. So this is something extra that shows up when you want to be dimension independent. And I know what you're thinking, yeah, I'm just going to work in 3 dimensions, so it's not going to make a difference for me, and I don't need these 2 types of approaches. But there's actually more to it. And to find out what, we will have to take a closer look at orientation. And so let us first define what we actually mean by orientation, because there are 2 completely different types of orientation. One is extrinsic orientation and the other is intrinsic orientation. Extrinsic orientation tells you how the space around your element is oriented. For a plane, that means it tells you which half of space is the up half and which half is the down half, or the front half and the back half, and so on. The other type of orientation tells you how the space inside your element is oriented. So for a plane, it means it's either going clockwise or it's going counterclockwise. And this actually is a property that exists for all types of elements. So for a line, it is intrinsically oriented when it goes from one end to the other or from the other end to one end, and it is extrinsically oriented if it rotates the space clockwise or counterclockwise around it. For points, they're a bit degenerate. The situation is a bit different. You're always on the outside, and you have these 2 types of spin that make up the intrinsic rotation. Now, why is this so important that you distinguish these 2 types of orientation? Well, when you reflect them, they behave differently. So if we reflect in a mirror that is parallel with our element, then extrinsic orientations, they will swap their sign. So the up arrow becomes a down arrow, the clockwise rotation becomes a counterclockwise rotation. For intrinsic oriented elements, when you reflect parallel to the element, the orientation stays the same. So here when we do this reflection, we're still moving in the same direction, and here we're still rotating in the clockwise direction. And the opposite thing happens when you reflect in an orthogonal mirror. So if you reflect in an orthogonal mirror, it is the extrinsic orientation that stays the same, and it is the intrinsic orientation that flips. Now, when you want to create, let's say, a line, you will want to either create a line with an intrinsic orientation or a line with an extrinsic orientation. And this is exact that same dual 2 ways of defining elements that we had before. When we create our lines by joining 2 points, we either join the blue point to the green one or the green one to the blue one, and this will trivially determine this intrinsic direction. And the same thing happens when we create a line by meeting 2 planes. So imagine that these are at a little angle, so you have this intersection line in between here. Then it would be oriented one way if we intersect blue with green, and it would be oriented the other way if we intersect green with blue. So these types of orientations are intricately connected with the way that you create them. The intrinsic rotations are created by joining elements, and the extrinsic orientations are created by meeting elements. So we will call these meet orientations and these join orientations. We'll call these join lines and these meet lines. And that'll be an important concept to keep in mind. It is particularly important, and all of the concepts that I've talked about in this episode are particularly important if we want to have a dimension-independent geometric treatment of dynamics. And so that's what we'll talk about now. Let's first sort of make a little overview of what we want. We want rigid body kinematics and dynamics in any number of dimensions. We, of course, want this unification of rotation and translation, but we also want to unify all of these other concepts from classical mechanics: force and torque, mass and inertia, linear and angular momentum, linear and angular acceleration, and velocity. So this first one, we've already figured out how to do that, right? To unify rotation and translation, what we need are these infinite elements. And we know when we add these infinite elements, we can view translations as rotations around infinite points. And we already know we can represent all of these as 2K reflections in parallel or intersecting planes. And that will give us all of the rotations and the translations. So what we'll look at next is the unifications of force and torque and mass and inertia. And we will introduce a concept called inertial duality to do that. So classically, forces are those things that generate linear motion, and torques are those things that generate angular motion. Now, when we look at what it looks like in PGA, it looks like this. So if we push a box at its center of mass, then we cause a translation. If we push it at infinity, we actually cause a rotation. If we push it at an arbitrary point, we cause a little bit of a combination of both. But what's important here is to note that these forces that are causing these motions, both the translations as well as the rotations, are always just forces along lines, right? So we don't need a force couple to generate a rotation, we just need to push at infinity. And that is an important concept, because this idea that forks are lines actually holds in any number of dimensions. But they are not just lines, they're actually dual to one another. So remember that when we were talking about duality, the infinite lines were associated with the planes that didn't cut the origin. And so they are the line that is normal to that plane is exactly above the origin. And so this is a local relationship. When you push at infinity, you rotate around your center of mass. So this is the origin of the box. If you have two boxes and you're pushing at infinity, then each box would rotate around its own center of mass. So let's look at that in 3 dimensions. And here we can again see the same idea. If you are pushing at the origin, you're creating a rotation at infinity. If you push at infinity, you create a rotation around the origin. And if you push at an arbitrary position, you will get a rotation here. But in all of the cases, this green line and this orange line, they are each other's dual. So here we're pushing at the origin and the dual line will be at infinity. Here we're pushing at infinity and the dual line will be through the origin. And if we push at an arbitrary point in space, the dual line will be here. So these guys, they are always join lines. A force is a join line, which is really easy. You just take the point you want to apply it to and you take a line through it, and that represents your force. And then if you dualize it in the body frame, you will actually get the center of motion that this force causes. The force causes an acceleration, and the acceleration will have an axis, and that's actually just the dual. So this is a tremendous simplification for the treatment of inertia. Now, when you want to do full inertia, we will require our object to have the center of mass at the origin and to be aligned with the principal moments of inertia, and then it's actually a dual map and some additional scaling. You can find all of the details in the papers. Right, so this gets us to the point where we can make a complete overview of what rigid body dynamics will look like, what a geometric picture is if you do it in a dimension-independent fashion. And then in the next episode, Leo will go into the algebra of all of this, and in episode 6 we will actually implement a simple rigid body dynamics engine together in PGA. But first, the overview. So we've just seen that forks, those are the lines you push along, and accelerations, those are the meet lines that you rotate around. They are each other's dual. So this classic way of formulating that relation, which actually uses a cross product, so you're really sure you can only use it in 3 dimensions, it completely goes away and gets replaced by this concept of inertial duality. Forks get integrated into momenta, and accelerations get integrated into velocities. This is the same way as you would classically do it. But again, this classic relationship that relates momentum and velocity gets replaced by the same inertial duality. And then all we need to do, of course, is integrate our velocity into our position. And this is linear and angular combined, so position is really position and rotation. And then the geometric picture, we've already said so, all of the forks are join lines through the contact point. So you can't have an easier way of doing this than just say, okay, you want to push somewhere, you take that point, you join it into a line with some other point, and this is your force acting at that point in the body. And then if we want to find out the acceleration that is caused by this force, we can just take the dual and we will get a meet line through the motion center. So if we push at infinity, our meet line will be through the origin. If we push at the origin, our meet line will be at infinity, which is exactly what this inertial duality does. When we integrate, for us as programmers, of course, that's just a sum of many small parts. So the momentum is going to be a sum of join lines, which isn't necessarily a line anymore, and the velocity is going to be a sum of meet lines. Then, of course, our position is going to be a motor, a 2K reflection, as we've seen before. This is completely dimension independent. So these join lines will always be d-1 vectors, and these hyperlines, because they're not always lines, they're only lines in 3D, so they're meet lines in 3D, they're always meet elements, but they're not always lines. In 2D, they will be points, but they will always be bivectors. And this is actually the complete picture. You have a very simple formulation of the Euler equations of motion that Leo will go into, and this is actually valid in any number of dimensions. So that's what we'll be doing in the episode 6. Okay, thank you.